Okay, hello everyone, and welcome to the lecture Multiphysical Simulation 2, take 2. Okay, our topic for today and the next two sessions will be induction heating, so magnetics heat coupling, and the topics we'll discuss today are the heat equation and how to handle nonlinearity in the magnetic field problem in frequency domain. Okay, then let's start with an overview where we use induction heating, or where induction heating is used in industry. So it's mainly used in like mechanical engineering parts, where you, for example, heat some gear wheels or some crankshafts, and mainly used to heat up the surface, or a thin region at the surface, which is then maybe cooled to increase the hardness of the material. And yeah, you can also use it for some deeper heating, not only in the surface region, but actually through heating to relieve some stresses in the material, and for annealing. So the basic principle induction heating is using is the heating by eddy currents. And so eddy currents are one part of the dissipative, or the power that eddy currents are using. The power loss is one component of the total loss, of the total dissipative loss in a ferromagnetic material. So in general, there are three losses that should be considered in ferromagnetic materials, and maybe I will give a short introduction to these loss components. So in general, when you look at the right at the tablet, the classical hysteresis curve looks the following. You have B over H. This is some idealized magnetization curve, and hysteresis means that we have an actual surface here in the BH region. Okay, another Delphin plot. Okay, so the area in this surface under the BH loop, given by, let's call it like loop H d B, if we consider it as a scalar problem, is the dissipative loss if we scale it by the frequency, meaning that's the work per one cycle of this hysteresis curve, or the loss per cycle. We can identify three different loss components of this total loss P. So this total loss P, or the loss per cycle, the P over F, actually consists of three very distinctive parts. So the first part scales with a constant. The second part of this power loss scales with the frequency, actually the frequency squared, because we scale the power by the frequency on the left hand side, plus another component scaling with the square root of F. And that's a very, very specific topic itself, active research topic, how you can actually quantify these three loss types. And these three loss types also, so this splitting is also called loss separation. And it's quite funny that it actually works like this, that you can actually split the total losses in a ferromagnetic material into these three components with different scaling factors of the frequency. And the reason for that is are the different length scales these losses occur. So this C0 component actually comes from the so-called Barkhausen effect, which simply means, or it's not that simple. I will try to keep it simple. This is based on Barkhausen effect. And Barkhausen effect means that there is a that the jumps of domain wall segments, so a jumping magnetization of very small parts of the domain, they're inducing eddy currents, because you have a magnetization which B is, call it mu0 H plus magnetization, and if this magnetization M is jumping, you have some time derivatives, and curl E Faraday is minus dB over dt. You induce some eddy currents. And you can also see this Barkhausen effect, so this jumps of very small domain wall segments in the hysteresis curve if you zoom in very closely. And most measurements don't resolve this effect, so it's not very common to see this in actual measurements. So let's again draw the hysteresis loop. It's really wiggly now, sorry. Hysteresis loop, and if you zoom in into this region here, you can actually see some stair-like behavior. So this is not a straight line, it's actually very wiggly, and that's a stochastic jumping of domain wall segments, the Barkhausen effect. So this is the C0 part here that scales with frequency if we multiply this whole formula with f. The next part, the next part of the error of the power loss, the C1 times f, is based on classical eddy currents as you know them from the exercise course maybe. So this C1 is based on classical eddy currents in your whole computational domain omega. So these are global losses that we will also consider as the main source of the dissipative power loss. So this is the main part of the heat source, scaling with frequency f. And the last part, the C2, scaling with the square root of f, this scales with f. These are the so-called excess losses. And they occur if whole domains, if whole magnetic domains are jumping. And so this is inducing then eddy currents in the size of the magnetic domains. So the size of these excess eddy currents is larger than the one of the Barkhausen effect, but way smaller than the global eddy currents in the whole domain. So you can actually plot this power loss behavior. If we plot P over F over frequency F, you first have the C0 part based on the Barkhausen effect, which scales with just C0. Then we have this part, so this is C0, then we have a linear scaling C1 times F based on classical eddy currents in the whole domain, and then we have an additional scaling, an additional part that scales with the square root. So this is C2 times F square root F. Okay, so these are the three components, and in typical frequency regions where we use induction heating, so in the maybe 10 to 100, 200 kilohertz range, the dominant part of the power loss, of the dissipative power loss, is this classical loss, so the classical eddy currents in the whole domain scaling with frequency. Okay, so let's go back to the slides. Okay, so there are two different types of induction heating processes. The first one is the so-called longitudinal flux heating, where the inductor is wound around the workpiece to be heated, and this placement of the coil results in a B field that is longitudinal to the heating to be for the workpiece to be heated. That's why it's called longitudinal flux heating. The opposite version is the transverse flux heating, where the B field is perpendicular to the sheet. And for these two versions, you're acting in different frequency regions. For the longitudinal flux heating on the left, the eddy currents, so if you want to heat very thin structures like sheets, if you want to heat solid material like a thick cylinder, this is not such a big deal, but especially for thin objects and thin sheet-like objects, the frequencies can increase very drastically, so in the 100 to 200 kilohertz range. And then it also gets a bit complicated to find, or to find power generators actually with that frequency, and that can provide some kilowatts of power to power the inductor. That's the reason why it is preferred to use transversal flux heating for heating thin objects or thin sheets, because then the frequencies of the impressed current don't need to be that high, because the eddy currents, the currents in the transversal flux heating, they are in plane of the sheet, as depicted here. They are in plane, and for the longitudinal flux heating, the eddy currents, they change direction in thickness direction of the sheet, and that's a crucial point, because if the frequency is not high enough, the eddy currents they cancel each other out. Only if the frequency is high enough that the skin penetration depth of the eddy currents is way smaller than the thickness of the sheet, then you can heat an object with longitudinal flux heating. Yeah. So it's based on Faraday's law, of course. Otherwise, there would not be any induction effects if there were no alternating fields. And the crucial point are the eddy currents. So the electrical conductivity gamma times E, or represented in a pure A formulation, it's minus gamma time derivative of the magnetic vector potential. And this term here, the Joule losses, J in E, or time derivative of A in time derivative of A scaled with the electric conductivity, that's a term we will discuss in a few minutes. Yeah, and especially for very high temperatures, if you want to heat up these objects to temperatures close to the Curie point or even over the Curie point, the solution dependency of the electric conductivity and also the temperature dependent magnetic permeability play an important role for moderate temperatures, so far away from the Curie temperature, as we will be dealing with in this lecture and in the exercise session. The only kind of nonlinearity we are considering is the solution dependent magnetic permeability, so the pH curve that I've previously drawn, but not the hysteresis curve, only the idealized pH curve. So this curve here, unique function, P over H. Okay. Yeah, then let's start with the heat equation first. Yeah, so this here is the first law of thermodynamics. I hope you've heard of it. So can anyone maybe explain in few simple words what the first law of thermodynamics actually is, or what it means? Have you heard about that in your study? Okay, does not seem so. So I will quickly go over the thermodynamics part. So the first law of thermodynamics is actually nothing else than the conservation of energy. And again, just a second. So the first law of thermodynamics is nothing else than the conservation of energy. And this conservation of energy can be written as a delta U. So this U is the inner energy U. It's a state variable. So it only depends on the end, on the final and initial state. So this can be written as U2 minus U1, and this is equal to a heat that we're inserting or that's flowing in or out of our control volume, plus a certain work, maybe some volume deformation work, like the integral of P dV. And this equal sign is the crucial point. So that's the conservation of energy. In differential form, we can write this as du is dq plus dw, and if we take the time derivative, we have du dt, time derivative dq, so time derivative of the heat plus the power. So this is the power, as you see here on the left side, and so this is the crucial point that we are dealing with. So this left hand side here can then further be investigated by inserting a caloric law. And caloric law, in this case, we're using du is Cp dt. That's where we introduce the temperature. And if we're inserting this into the first law of thermodynamics, so this small u, actually the caloric equations are written in specific values. So this u here, this u is scaled with the mass density rho, as you see here in the slides on the left. So we have the time derivative of the global inner energy as time derivative of the integral, where we scale a specific inner energy with mass density and insert the caloric law. The next step is that we're using Fourier's law. And Fourier's law simply is the heat flux density vector is the negative gradient of a heat conduction coefficient, which can be temperature dependent, or which is temperature dependent. The question is if we neglect this temperature dependency or not, times the gradient of the temperature field. Okay. So this is the final form we get out of the first law of thermodynamics combined with Fourier's law. And what's left is this right-hand side. And this right-hand side can be used as some kind of forcing, or some kind of power delivery that we're delivering into our control volume. And in our case, the control volume is the workpiece we want to heat. And this Qd, the dissipative power loss density, or dissipative heat density, that's the variable we are putting into our system via the eddy current losses. Okay, so this is the heat conduction equation, and furthermore we can also include a convective term into the heat equation. So if we consider the sheet that we were discussing before, not in a non-moving form, so we want to let the sheet move in one direction, we can introduce this movement with a certain velocity v into our heat Pde, which is then not only a diffusion Pde, as this is here. So here, classical diffusion Pde, we have if we set this lambda, the heat conductivity, as homogeneously distributed, so we can pull it out of the divergence operator, then we have a simple Laplace operator here acting on the temperature, a time derivative on the temperature, so that and the forcing vector, of course, the Qd, and that's the typical diffusion Pde, so heat Pde. Then we can include this convective term via Reynolds transport theorem, and this Reynolds transport theorem works the following way. I will quickly show you what's the Reynolds transport theorem. So let's consider it in an abstract way. So we have a scalar quantity, which can be temperature or the electric scalar potential. Then we define the rate of change of this scalar variable in the whole domain, in our whole computational domain, as the integral over the time derivative of the local quantity plus what's being delivered inside or outside of the computational domain at the boundaries. So we have this phi times v in n. So that's this v is the velocity of the quantity phi at the boundary. And if we set this phi to rho u, so here u is the inner energy as before, the specific inner energy. So if we insert this, we have the time derivative of rho u plus the boundary term rho u v in n. And then there are some steps in between that I will not show you now, but here we'll be using the first law of thermodynamics. We'll use Fourier's law and the caloric law, and then we end up with the following: minus the boundary term lambda gradient T, so the Fourier's law in n, so the heat flux density vector at the boundary, plus some volumetric heat sources, which, by the way, this is du over, so that's capital U, the total inner energy rate of change is right hand side time derivative of, so that's the caloric law, rho Cp T plus the boundary term as we had it, d omega rho Cp T v, the velocity in n. Okay, now we can use Gauss integration theorem. Come on, why isn't it working? Okay, so we can use Gauss and can rewrite this boundary term as minus integral divergence of lambda gradient T plus the volumetric heat sources is, and we can copy the right hand side. There's no change. No, we rewrite the boundary, of course. So this stays the same. That's d over dt rho Cp T plus, now we use Gauss law again for this boundary term and have the divergence of rho Cp T v. Okay, then we can simplify these expressions by saying that Cp, rho, and lambda are not space dependent, so they're the same in all regions. Then we can pull them in front of the differential operators, divide by rho Cp, and get the following: lambda over Cp rho times the integral, and we want to get rid of this integral, which is not a big deal since we can assume here that this formula has to hold for every infinitesimally small volume element. So we can write it in differential form, and then it is simply the divergence gradient T. Maybe I'll switch to Nabla notation. So we have the divergence of gradient T plus 1 over rho Cp Q dissipative power losses is time derivative, the temperature plus the divergence, plus divergence of Vt. So that's nearly it. We can then identify this term here as our c squared, the diffusion coefficient, and end up with the convective diffusion equation in its final strong form as time derivative of t times divergence of velocity t is minus c squared Laplace, so divergence gradient t plus 1 over rho Cp q dissipative. Okay, so this is the final form of the convection diffusion equation. So heat Pde with convection. That's the way how to obtain this formula here. And it's all based on the Reynolds transport theorem and on Gauss law. So that's not a big deal. Okay, then we have, as I've already mentioned, we have some solution dependency of our material parameters. So we have a solution. We have a solution dependency of the thermal conductivity. So this is not conduction; it's thermal conductivity lambda, and a temperature dependency of the heat capacity. And in fact, there is actually kind of a, I would say, heuristic law called the Wiedemann-Franz law that connects the electric conductivity and the thermal conductivity via a certain multiplication factor. So we can, if you know the temperature dependency of maybe the thermal conductivity, then you can approximate the electric conductivity by multiplying this behavior with I think it's called the Wiedemann factor or something like that, but it's material dependent. So this factor you have to know, or of course you measure both quantities temperature dependent. Okay, yeah, then we have, as always, have to deal with boundary conditions. So that's the annoying part, but since this convection diffusion equation is not that difficult and we're in an easy function space, we have scalar variables, the boundary conditions are not that difficult, so not as difficult as in the magnetic case. So we have, again, as always, theoretically boundary conditions where we can prescribe the temperature at a certain boundary. We have Neumann boundary conditions where we can prescribe the normal derivative of the temperature at the boundary, so we can prescribe a heat flux vector. We can have a convective heat transfer, which is given by this formula here. So the difference between the Neumann boundary condition, where we prescribe the heat flux vector with a given value, the convective heat transfer boundary condition, the problem is that we don't know the right-hand side. So we do not know the quantity of the heat flux over a surface. This heat flux is depending on the temperature difference between the solution quantity, so the temperature at the boundary where we want to apply the heat transfer boundary condition, and the surrounding maybe air temperature. So we have to prescribe something where we don't know this, that we do not know yet. So this will be assembled into our system and handled that way. And of course, the combination of Dirichlet and Neumann boundary conditions, Robin boundary conditions, where we can either prescribe, and prescribe the actual value and also the derivative in normal direction. Okay, but this is not a big deal in this course because it can maybe model the contact between two different materials with different heat conductivities or thermal conductivities. Okay. What I've not told you is that the convective term, so this term here can lead to some instabilities in the numerical solution, especially because it the final system matrix, if we perform the classical weak form of this heat convection Pde, discretize it with H1 nodal elements, so classical Lagrangian finite elements, and write down system, the linear system, we will see that the system is not symmetric. So the system matrix is not symmetric, and this can lead to some severe instabilities, especially if the velocities are high. Okay, and I've prepared a small demonstration example where we use CFS to actually show this instability behavior. So the problem we are considering looks the following. We have a simple 2D domain meshed with quadrilaterals, and we prescribe a temperature here on the left. So that's a Dirichlet boundary condition that we're prescribing here, and a Neumann boundary condition on the right side and on the top and bottom side, or of boundaries. And then we consider a heat source right at the center of this plate, which you can think of as maybe holding a torch beneath a metal sheet and moving the metal sheet over the lighter, over the torch. Then the resulting temperature field might look like this. So this is already computed with a higher velocity, and you can see the solution. This is the steady state solution, so the solution for t for time towards infinity. And we can now play with the velocity and observe the solver parameters. Okay, so let's open the simulation file. And here we are defining the velocity. In this case, the velocity of the region, so of the sheet, is 1 e minus 4. So maybe let's switch it to 1 e minus 8. So smaller velocity simulated. Sorry. Okay, and let's observe the solver statistics. So this was the computation with a small velocity. I will copy the solver statistics. So we're using a direct solver in this case, a Paradiso solver, which is a very fast direct solver, and a solver that can handle really dirty systems, as this one is. So I'll copy that into this editor, and now we change the velocity back to a higher velocity and simulate it again. And now let's compare the solver statistics. Yesterday when I tried it, it worked. I hope it does now as well, since my fan is blowing at really high RPMs, so I guess the CPU load is quite high as well. Let's check it out. So on the right hand side we have small velocity, on the left hand side we have higher velocity. So Paradiso, the first phase is the reordering phase. That should not be any major differences, and if we compare it, the reordering times are not that different, and yeah, and let's go on to the factorization. That's the region, that's the phase where we should see the differences, hopefully. Okay, so here time spent in factorization. Here we have the higher value for the higher no, sorry, it's smaller actually. Okay, yeah, maybe we can, no, that's smaller. That's strange. And yeah, which velocity was this? Thermal. Quick, this was 1e minus 4. So this was a higher velocity. Maybe we increase it even more. We have to see a difference, I hope. And simulate it again. The factorization, and now we see a difference. So the factorization phase left at the high velocity, right at the low velocity. And we see an increase in factorization time and also in the total time, factorization total time. The solving might be influenced as well, but not as dramatically as the factorization. In fact, it's actually a little bit faster. Yeah. But we can observe it a bit clearer if we look at the system matrices directly. So I write the system matrix as an output result, and I'm reading in the system matrix, which is written in matrix market format. And let's have a look at the matrix, at the system matrix that we're solving, which looks like this. It's a banded structure. This is after the reordering. So the pure assembled matrix looks way different, but that's not what I want to show you. What I want to show you is, let's have a look at the entries of this matrix. So here you see the first diagonal, and the off diagonals are symmetric, which is this middle line here. Then if we continue to the first off diagonal block here, so we move to the right, where is it? Here it is. Here we have a value of minus 2.3 E7, minus 5.9 E6, and if we observe the value at the transposed side, so at the lower off diagonal, you see different values. So they have opposing sign. So that's where the non-symmetric behavior comes from, and that's the part that makes the solution of these systems, especially if they're larger and 3D and the velocity is high. That's the reason why you might run into some problems with your solver. Okay, let's close this and go back to the sheet, to the slides. Okay. Yeah, you can increase the time integration order by maybe using a higher order integration rule, maybe trapezoidal or a quadratic integration rule, and maybe change your integration scheme at all. So maybe use an implicit solver to overcome this problem. Okay, so now let's continue with the coupling to the magnetics part. And as I've said, this dissipative losses, so the heat, actually the heat sources, the right hand side in our heat Pd or convective heat Pd, are consisting of eddy currents. And this is simply the time derivative of A in time derivative of A scaled with electric conductivity. So we first need to compute the A, or solve for the magnetic vector potential in the magnetic step. Then we evaluate the Joule losses. So we evaluate the time derivatives and perform a scalar multiplication. Then we have a scalar quantity that we can prescribe as the right hand side of our heat Pde. So this is shown here in this scheme. So if we don't have solution dependent conductivity, we can, so electric conductivity, we can simply set it to a fixed value, perform one magnetic step, which can be nonlinear. So it can have a solution dependent magnetic permeability. So we're iterating here how we solve that. I will show you in a few minutes. So if we have a solution that we're happy with, we evaluate this Joule loss term. So we have the dissipative losses available. We insert these losses as the right hand side in our heat convection Pde, and we solve for the thermal problem. If we want to include temperature dependent electric conductivity or temperature dependent magnetization curves, we then have to loop it back, evaluate the material law for the conductivity and or for the permeability, solve the magnetic problem with the updated values again, and iterate until we have a solution that we consider as okay. Yeah, what's the problem, or why is this problem more involved? So this coupled problem more involved than you might think. The reason for that are the time scale differences between the magnetic and the thermal problem. So if you consider an alternating current with a few hundred kilohertz in the inductor, and you want to heat up a workpiece, like maybe a solid workpiece, like a crankshaft of a car, which is a solid piece of steel, then it's not heating it up in maybe 1 second. Yeah? It needs a few seconds to increase the temperature, especially if you're simulating or if you want to heat up the core of the material. So it takes some time until the temperature diffuses into the core. So you have quite large time constants in the thermal part, and very small time constants, very small time periods in the magnetic field. So you want to kind of decouple the simulation of both problems, so you don't want to solve both problems in time domain, because maybe you want, if you're considering the magnetic problem as nonlinear, you want to resolve one period of the magnetic problem with maybe, I don't know, 20 or 30 time steps, and they are completely unnecessary for the thermal problem. For the thermal problem, it would be sufficient to update the solution, or to solve the thermal problem every second instead of every microsecond, as we do in the magnetic problem. So that's the crucial point in this coupled problem. And the way we do this is we transform the magnetic problem into frequency domain. We solve the magnetic problem in Fourier space. So we're getting the steady state solution. So the steady state solution is the solution that a transient simulation would be for if you simulate for an infinitely long time. Okay, and how is it done? That's not a big deal. So we're starting off with the classical curl problem here, with a solution dependent relativity. So this new magnetic relativity is depending on the B, on the magnitude of B, and we also have the eddy currents, the eddy current part here. So that's the eddy current problem with a prescribed impressed current density. And if we want to transform this equation into frequency domain, we cannot simply multiply this or replace this time derivative with a j omega, because we have this nonlinearity here. So in fact, we have to transform, or we have to apply a Fourier series expansion not only for the magnetic vector potential, but also for the magnetic relativity. So we have this Fourier expansion, Fourier series, truncated Fourier series of the magnetic vector potential. We can rewrite it to make it a bit more likable to get a good numerical scheme out of it. And we do the same thing with the magnetic relativity, and we expand each part, so the magnetic vector potential and the magnetic relativity, in these truncated Fourier series. We insert them into the eddy current problem, and after some derivations, we end up with a linear system. And the way how to obtain the linear system is actually straightforward, since we multiply this eddy current problem in frequency domain with the inserted Fourier series, truncated Fourier series, or Fourier expansions. We multiply it with e to the power of minus j omega nt, and this n here is going from minus n to n. So these are the maximum number of harmonics we are using to expand our vector potential, and we integrate over one period length, over this omega 2b over omega. So yeah, so we're averaging the power over one period, and that's if we solve this, we have the power. If we solve then for the Joule losses, so the J in E, we have a steady state Joule loss that we can prescribe into a transient thermal problem or a steady state thermal problem, so that this does not matter afterwards, since we're using averaged period, averaged quantities here in the magnetic problem. Okay, then we can explore the property that if we're integrating this exponential function over one period, it is 0 if this exponent is not 0. So in case for this exponent to be 0, we need in this case the k plus m to be equal to n, and the same thing occurs for the k minus n exponent coming from this term here. We perform integration over one period and get this result of 2 pi over omega if this exponent is 0. And then we can let this n run from minus n to n and get the rows of this system. So maybe I will write this down for one particular n, so that you see how the first line is derived. Then all other lines follow according to this scheme. Okay, so maybe I'll do it side by side. Okay. Yeah, let's start with the first row where n is, so small n is minus capital N. So this first line here. And if we set this n to minus n, the question is which combinations of k and m are solving this equation. K plus m is minus n. So this is the small n. So of course we can then loop through all different k's and m's. So for k equal to minus n, the m would need to be 0. For k minus n plus 1, m needs to be minus 1, and so on. So we can write this permutation thing here as a matrix, as a vector multiplication. So we say the curl of a vector consisting of the Fourier modes of the magnetic relativity signal. So we have 0 that we have to multiply with the a exponent minus n. Just a second. So then there is nu minus 1. It will get clear in a few moments, until we're expanding nu until capital M. And we multiplied this nu vector. There should be zeros afterwards to get the dimensions right. And we multiply this vector with the vector of curl A. So the first exponent, so index 0, must be multiplied with the n exponent minus n. So this is the A minus n harmonic. Then curl A minus m plus 1, and so on, until curl A plus n. And of course the mass term, but the mass term is straightforward. Since k is n, it's not a big deal. It's a diagonal matrix. So this here is the first row of our matrix, well, the first portion. So curl nu, this should be a minus m, sorry, multiplying with the vector of the curl of the A harmonics, and then we exactly reproduce this formula for every n. Okay, so this is I would call it a pseudo strong form of the nonlinear nonlinear eddy current problem. If we then start discretizing it, and discretizing the weak form especially, then we end up with a final linear system that looks like this. So this first block, or this first matrix of matrices, comes from the curl term, so the stiffness part, that's the stiffness part. The next part comes from the, let's call it mass part. In mechanics, this construct is called mass matrix. It's a diagonal matrix coming from the time derivative term, from this term here. That's where the M matrices come from. And of course we have a right-hand side consisting of our impressed current densities in the different harmonics. So we can excite the problem in all harmonics from minus n to n. So the problem is, it looks not that difficult, but it is actually very difficult to solve this system, since it is huge, because every K matrix here consists of all spatial degrees of freedom of the whole computational domain. So if you discretize your domain with, I don't know, 1 million elements, this K matrix and all K matrices have a dimension of, yeah, let's approximately say 1 million by 1 million spars. So these are huge systems. And in order to solve this huge system, we need an efficient solution strategy. And in our case, we use a nested iteration strategy for the outer and inner iteration. So the outer iteration, for the outer iteration, we use a damped fixed point scheme, and for the inner iteration, we use a preconditioned GMRS or conjugate gradient solver. The GMRS is working a little bit better here in this case. And speaking about Jacobi preconditioner means we're inverting the diagonal entries of a matrix. And since we're dealing with matrix of matrices, we not only need to invert certain entries, we need to invert whole matrices. And since inversions of a matrix in C are bad per se, we're using a direct solver to kind of circumvent this inversion of the matrix, and for this behalf we're using Paradiso. Yeah, the problem is, or we can, if we assume certain assumptions, we can decrease the size of this whole system dramatically. So in this case, if we don't perform any kind of assumptions, the system consists of 2n plus 1 solution vectors. Yeah? So every n as well as every k consists of all degrees of freedom of your whole computational domain. So that's the solution vector for all harmonics. And we can in fact decrease the size of this solution vector and the whole system by a factor of approximately 2, because we use the following. Maybe I'll go back to the tablet again. page. Okay, so how can we decrease the size of the system? Let's consider the pH curve, so the Hysteresis curve first. We have the P and the H. We're not considering any hysteretic effects, just this idealized Hysteresis curve. And the material parameter we're using in the simulation is the magnetic relativity. So the derivative, the permeability, is defined as the dB over dH, and nu is 1 over mu. So if we plot the nu over B, we plot this results in, we have a non-zero value here. We have our vacuum relativity nu 0 as an upper boundary, and the relativity looks like this, and also in negative direction. Okay, so that's the nu curve. You have seen, I think you have seen that in the previous lectures of Professor Kaltenbacher, where this nu curve had a slight kink here, and I will discuss this in a few minutes. Just a second, I will. Okay. The reason why it is important that this curve does not have any kinks at low B values, I will explain in a few seconds. The crucial thing is, if we plot the nu again in this graph over B, yeah, that's a bit shitty. Okay, that's our time coordinate. Time, come on, and maybe we prescribe a sinusoidal B field. So maybe we say we excite this nu of B function with a sinusoidal B. So that's our input signal. That's the B of t, and we use this nu of B as kind of a black box material. So the B of t is our input, then we have the material, and the output is the nu of t. And if we plot this nu of t and nu, we see the following. Like, this is the time period of the B signal. One and the left part. Okay, so here that is the period length of the input signal, and this actually half period is the period length of the nu signal, and it's also it's an even function. And if we perform a Fourier expansion of this even function, all odd harmonics in the we only get out odd harmonics, and the even harmonics are 0. So we can skip all even harmonics, so nu minus 2, nu minus 4, and also the transposed values nu 2, nu 4, and therefore we can decrease the size of this of the system dramatically. Okay, in a few seconds. So it's not done, so that the solution of the whole problem is not done by solving this system one time. Yeah, we need to solve this system for every adaptation of our nu. So you can see the nonlinearity actually by these off-diagonal entries. So we're coupling different A harmonics with each other, and that's the way how we introduce the nonlinearity into our system via these off-diagonals. If these off-diagonals were not there, this would be a linear problem, a simple harmonic solution for frequencies of minus n omega d to plus n. Yeah? And because we are introducing these off-diagonals, we get the dependence of A and the dependence of different A harmonics. And the dependence of A and nu is introduced via the material law. Via the material law. So the kind of evaluation of this of the pH curve. So the whole solution strategy looks the following. So we're starting with an initial relativity, like maybe a linear relativity, or some secant modulus of the pH curve. So our initial value, and we're solving a linear harmonic problem with this chosen initial nu to get our harmonic solution for one harmonic. So that's a classical harmonic solution. So we replace the time derivative with j omega, and that's it. You're solving for one frequency. The solution. So this should be the A harmonic in frequency domain. We're transforming this into time domain to get the A of t, respectively the B of t. Then we evaluate the pH curve, we evaluate the nu of B curve. We get the nu time signal. We Fourier transform, or we FFT the time signal of the nu, and get the harmonics of the magnetic relativity that we're using to assemble this system here. So we get the nu minus m to nu plus m. We set up the system, or assemble a system, solve the system with nested iteration strategy. Then we have an updated solution. We transform it back into time domain, evaluate the material law, and cycle until we're happy with the solution. So that's how we introduce the coupling of A and nu. Okay. Okay. So this whole scheme is called harmonic balancing. There are different, I should mention, there are different ways to actually perform harmonic balancing, and this particular scheme is called alternating time frequency. Okay, then I have 5 more minutes. Okay, then I have provided a small example of what happens if you provide the wrong material model. So in this case, the heavy metal sandwich, as I've named it, we have a current carrying a current carrying layer where we impress a current density and some conducting layers at the top and bottom surface of this current layer. And this omega iron has a pH curve, so a magnetization curve, and we're solving this in frequency domain, so with the multi-harmonic ansatz and harmonic balancing, as well as in pure time domain. So we're simulating for a very long time until we are totally sure that that all transients are vanished, so we have a reference solution. And now I want to talk about the topic that I've mentioned, that this material model is simply wrong if you are looping from saturation to saturation in the third quadrant, because if you think about moving up and down on the hysteresis loop, there is no change of the no certain change of the permeability, respectively relativity, at small field regions. So this kink here is simply wrong, and the reason why many people use these wrong material models is because this is the result of the so-called commutation curve, which is depicted here with the dots. So in hysteresis measurements, if we're measuring hysteresis curve with an increasing amplitude, excitation amplitude, you're measuring larger and larger hysteresis loops. And if you connect the I don't know the English word, the Umkehrpunkte of these minor loops and connect these points, then you get the commutation curve. And this commutation curve has this kink at low field strengths. And this region here is called Rayleigh region. But for a harmonic simulation, or if you're cycling from saturation to saturation, there is no Rayleigh region transforming your permeability or altering your permeability. So this is actually the wrong material model, and the correct material model would be the so-called anhysteretic curve, or idealized magnetization curve, which is simply thought of as if you narrow the loop until the area becomes a line, then you don't have this this Rayleigh region effect here. So the difference might look negligible as it is shown here in this graph. So these are actually measurements that I've measured on an Epstein frame. So the commutation curve in turquoise has this Rayleigh region here, and the anhysteretic curve, where a different measuring procedure is used that I will not show you now, we don't see this Rayleigh region. This is the correct material model that we're using for multi-harmonic simulations. And the effects of this, what might seem negligible difference between the commutation and the anhysteretic curve, can have quite severe effects on your solution, especially if you're solving with the multi-harmonic ansatz. So on the left, we're using the commutation curve with the kink in the magnetic relativity at low p values, and on the right we're using the correct anhysteretic curve. So in turquoise is that's the nonlinear transient solution, so the reference solution. And with the multi-harmonic ansatz, we really need to increase the number of harmonics to somehow get close to the reference solution. So even if we're using 21 harmonics, we still see some oscillations which should not be there, but they occur simply because of the wrong material model. With the correct material model, so the anhysteretic curve, we already get a really good solution with only 3 harmonics. So you don't see much difference between the turquoise line and this orange curve here. And this with the large amplitude, the colors are a bit misleading. With the darker turkey, or the blue curve here is simply a linear simulation for reference to see that there is actually a flattening of the B, which means that's the saturation region. Okay, so always take care that you're using the correct material model. Yeah, okay, not so bad in time. This already brings me to the end of today's lecture, and next time we will talk about eddy currents and skin effect, how to approximate the skin depth, and I will show you an actual application example of a project where we were using this multi-harmonic ansatz and harmonic balancing framework to simulate the heating of a thin steel sheet, and we were also comparing it to measurements. And I will provide the homework questions next time. Okay, then thanks for your attention. Are there any questions?